This lecture is about stoichiometry, and stoichiometry is all about the mathematical relationship between quantities of reactants and quantities of products. And it's a mathematical method that scientists use to calculate how much product could be made starting with a given amount of reactant. There are some basics you need to understand first about a chemical reaction. Sorry if I'm talking below you, but everything on the left side of the arrow is a reactant. Everything on the right side of the arrow is a product. The arrow itself means yields. So this reaction, for example, you need to get used to using the nomenclature you learned in the last chapter. So this happens to be methane. That's its common name, but its real technical name would be carbon tetrahydride. Reacts with oxygen to yield carbon dioxide and 2 molecules of water. Excuse my dogs, please. And the visual here is just showing you the molecular models so you get familiar with seeing those. But what I want you to start paying attention to now when you see these reactions are the large numbers in front of each chemical. If there's no number, it's understood to be a 1. And so it is these numbers that are called coefficients that we'll use to do our stoichiometry calculations. A chapter or two ago talked about the law of conservation of mass. And the textbook definition of that is that mass is neither created nor destroyed. And so that has important implications in a chemical reaction. Because basically what that means is if you have reactants and together they have a mass, let's just make up a mass of 50 grams. And they react to give you two completely new substances. It turns out that the total mass of the new substances must also be 50 grams, okay? So that's an important understanding of the law of conservation of mass. And you might actually see a multiple choice question like this that asks you to predict the mass of product made, and you would use the law of conservation of mass to do this. It's important to point out that before doing any stoichiometric calculations, you must have a balanced equation. When you balance a chemical equation, you get the coefficients, those large numbers in front of each chemical, correct. And until you get those correct, none of your stoichiometric calculations will be correct. Sorry about that. Think of the coefficients as representing molecules or moles or anything that you can count. So this would be 2 molecules. This happens to be octane, and reacts with 25 molecules of oxygen to give 16 molecules of carbon dioxide and 18 molecules of water. This happens to be a combustion reaction, which you need to commit to memory. It's one of the more common reactions we see in chemistry. And I would write down a couple things about a combustion reaction. It's one of the reactants is typically a hydrocarbon. That is a compound that is made up of carbon and hydrogen. To be a combustion, it must react with molecular oxygen. Okay, so it's like you burn anything, it needs oxygen or the fire will go out, right? And the products of combustion always are carbon dioxide and water. And so that's an important one to just commit to memory. You could also read this balanced equation. Instead of saying molecules, you could read it as moles. Okay, so if you're saying 2 moles, basically you're saying 2 times 6.02 times 10 to the 23rd molecules. Okay, but basically these stand for anything you can count. So the first concept you're going to learn before we start doing stoichiometry is what we call mole ratios. And mole ratios are gotten from the coefficients in the balanced reaction. Okay, so if I asked you, for example, what is the mole ratio between octane and oxygen, you would simply go to the balanced reaction and you would say, okay, the mole ratio of octane to oxygen is 2 to 25. You just go to those substances and look at the coefficient, and then you get the mole ratio. What if I asked you, what is the mole ratio of carbon dioxide to water in this reaction? You would say it is 16 to 18. You could simplify these mole ratios if you wanted and say it is 8 to 9. So you should be able to come up with a mole ratio of any reactant to any other reactant or any reactant to any product, because we'll use all those mole ratios in various stoichiometric problems. So here is a very basic stoichiometry problem. Using the same reaction that we've been talking about, the combustion of octane, this question says, if we start with 22 moles of octane, and so I've gotten in the habit, I pretty much write the amounts and the balanced chemical reaction. It just helps me visualize. If we have 22 moles of octane, how many moles of carbon dioxide can be formed? Now, if you have a math type brain, you may be able to just look at that and know the answer, but I guarantee you very quickly you won't be able to do it in your head. So you really need to learn the process by which we calculate stoichiometry problems and stick to that process closely. You will need to show your work in this type of manner to get credit on tests. So get used to doing it, please. So we did a little bit of dimensional analysis or unit cancellation in chapter 2, I think. We're going to use the same type of method. So we're going to start with the given information, the problem, which in this case is 22 moles. It's important in stoichiometry problems to actually write moles of what. Don't just stop with moles, because there's, as you can see, all different substances we're working with. So that's moles of C8H18. If you're more familiar or more comfortable with this kind of T diagram, I can do that. And then what we use when we're trying to figure out how much product a reactant can make is we use the mole ratio is our conversion factor, okay? That's what allows us to convert essentially from a reactant to a product, or any one substance to any other substance. So we need to match units on the diagonal so that they cross out. And so moles of C8H8 needs to be down here in the denominator. And what number goes in front of C8H8? The coefficient in the balanced reaction. So 2 moles of C8H, whoops, that's 18, gives 16 moles of CO2. Okay, and that CO2, the 16 comes from here. And this problem is that simple. So you see now that moles of C8H18 cancels out. It's on the diagonal as it should be. And our math problem now is 22 times 16, all divided by 2. And if you do that math, what you end up getting is 176 moles of carbon dioxide is formed when you burn 22 moles of C8H18. I gave you a mole map when we were doing mole calculations, grams to moles, molecules to mole. Here's a stoichiometric map. And basically what I want to emphasize here is if you are given in a problem the grams of one substance, usually a reactant, but it doesn't have to be, and you're asked to find the grams of a different substance, you cannot go directly from grams of one substance to grams of another. Every substance has a different molar mass, and therefore you can't, it's like comparing apples and oranges, you can't do it. You need to get both substances to moles, and once you have moles of each substance, then you can use the mole ratio to compare those two. So the bottom line is a typical stoichiometry problem will start with grams of one substance, Every arrow, remember, represents a calculation. So your first calculation will typically be to calculate moles of the beginning substance. The second calculation will be to use the mole ratio to get to moles of the new substance. And finally, the third calculation will be to get from moles of the new substance to grams of the new substance. So many stoichiometry reactions are three-step calculations. If you're feeling confident already at this early stage, then I want to encourage you to turn the video off for a moment and try to work this out. That would be awesome, but it's unusual. Don't feel bad if you're overwhelmed and have no idea what I'm doing yet. You will, I promise. It takes a lot of practice, though. So let's go through this problem step by step. Let's first get what we can out of the problem. So here's the reaction. Always check to make sure the reaction is balanced. If there are coefficients in front of the substances, you can presume it's balanced. So what is the given information? 25.5 grams of potassium chlorate. You need to be able to figure out what potassium chlorate is. That's this. I always write the given information down. So we have 25.5 grams of that. And what is the problem asking for? It's asking for moles of oxygen. Okay? So I need to go from grams of potassium chlorate to moles of oxygen. So I would jot that stoichiometry map down on the last slide if you didn't already. But what it shows us, if you start with grams, and in this case it's potassium chlorate, step 1, calculation 1, is to go to moles of that substance, so moles of potassium chlorate. Step 2 is to use the mole ratio to go to moles of the substance we're interested in, or what the substance they're asking for in the problem, which is oxygen. And in this case, we only have 2 calculations because the problem is asking for moles of the product, not grams. If the product were asking for grams of oxygen, we would have a third step. So let's go through the calculation. We start with the given information, which is 25.5 grams of potassium chlorate. If you're more comfortable using the T diagram, you can do that. And then the first calculation we need to do is go from grams of the substance to moles of that same substance. And you hopefully remember from last chapter that to go from grams to moles, we use molar mass. So 122.55 is the molar mass of potassium chlorate. Okay? And so that's adding the mass of 1 potassium, 1 chlorine, and 3 oxygens together. Now you can see that grams of potassium chlorate cancel out. Whoops, I shouldn't have canceled the number, just the grams. And the math ends up being 25.5 divided by 122.55. And our answer for the first calculation is 0.208 moles of potassium chlorate. It's a good idea. I know this is too many sig figs at this point. It's a good idea to carry extra sig figs until you're all done with the calculation and then round it correctly to how many sig figs you're supposed to have. All right, so here's the second calculation. That is to go from moles of the substance we started with to moles of the substance the problem's asking for, which is oxygen. We always go from moles of one substance to moles of another using the mole ratio. We get the numbers in the mole ratio from the coefficients in the balanced reaction. So moles of potassium chlorate, means that we need moles of potassium chlorate in the denominator here, so the units cancel. And this 2 comes from the 2 in the balanced equation. On top are the moles of the substance the problem's asking for, which in this case is oxygen. The 3 comes from the 3 in front of the oxygen in the balanced reaction. So our math now is 0.20808 times 3 divided by 2, and that gives us 0.312 moles of oxygen. And that's all the problem asked for, was moles of oxygen. If the problem asked for grams of oxygen, we would have a third step, which we would go from the moles of oxygen we just calculated and convert that to grams by multiplying by molar mass of oxygen. Be careful when you're using the molar mass of oxygen. Remember that it's diatomic. It's important to memorize the 7 diatomics, mainly for this reason. I would strongly recommend that you give this problem a try on your own. Even if you're feeling kind of insecure, go back to the last slide where I worked out the last problem and give this a try on your own. You do need to write a balanced reaction out first, okay? It's combustion, so that's important. That's something you need to be able to get out of this lecture, to write a balanced combustion reaction. So that's your first goal, is to write the balanced reaction. And your second goal is then to work the stoichiometry problem. And if you can do those 2 things, you're in really, really good shape. I will have the problems, both those steps worked out for you in the next slides. The balanced reaction looks like this. So you do have to remember that oxygen is always a reactant. Oxygen is also diatomic. Carbon dioxide and water are always the products of a hydrocarbon combustion. You may have had trouble balancing this. If so, try to go through and make sure that you understand how to do it. I'll give you a tip again for balancing combustion reactions. Balance the atoms in alphabetical order. Carbon, then hydrogen, then oxygen. I call that the CHO rule. And so here's the balanced reaction. Now, the given information started with 1 gram of glucose. And if you remember, of course, our little stoichiometry chart said go from grams of the first substance, to moles of the first substance. And then from moles of the first substance to moles of the second substance. And finally, in a third step, from moles of the second substance to grams of the second substance. So that is 3 calculations. So first, and again, just so you're kind of familiar with your t-square here, we use the molar mass of glucose. It's 180. Hopefully you got that right. To convert from grams of glucose to moles of glucose. What I've done here is I have a run-on calculation. This is one calculation, here is the second calculation, and here is the third calculation. You can do them each separately, or you can do them all together like this. Notice the units have to cancel on the diagonal for each step. Okay, so the first step is going to moles of glucose. The second calculation is using the mole ratio to get from moles of glucose to moles of water. And the third and last step is using the molar mass of water to get from moles of water to grams of water. So the math equation ends up being 1 times 1 times 6 times 18 in the numerator. And a lot of students tend to mess up this calculation using their calculator. So make sure you got it right. Take a minute, make sure you know how to use your calculator correctly. In the denominator is 180 times 1 times 1. If you enter that correct in your calculator, you get that burning 1 gram of glucose, which is essentially sugar, produces 0.6 grams of water. If you're a visual person like I tend to be, here is the calculation process in terms of the stoichiometry map. So we went from grams of glucose. Remember, you can't go from grams of one substance to another. It'd be nice if you could, but you can't. The first calculation is using the molar mass of glucose to get to moles of glucose. So if you did it in 3 separate steps instead of a run-on calculation, this would be one of your intermediate answers. The second step was using the mole ratio to convert to moles of water. And the third and last step was using the molar mass to convert to grams of H2O. That's it for stoichiometry. It does get more complicated in this. The next thing I'm going to learn is something called limiting reactants. And so I'll see you in the next lecture.